Hello guys and welcome to another video with Cass on the Maizuma channel. Today we're going to talk about basic microcontrollers. In one of my videos I showed you guys how you can make this setup with a button and a LED to behave like a T flip-flop thing. There were some problems and I teased you guys in the end of the video by showing you that a microcontroller solution could sort things out. So today we're going to talk about those two microcontrollers, but not in too much detail. This is just an introduction. So a microcontroller is an active component, meaning it can execute instructions that we put inside it. This one has room for very few instructions, so only 9 instructions in total, and it has one variable called the accumulator, which is this little box in here. But you will be surprised that you know how many things you can do with just one variable. It's really cool. Okay. So we know that we can execute instructions, but microcontrollers also have connections to the outside world. So it does that by having those pins in there that you can connect to different devices. In this case, this is a MC4000 microcontroller. It has two different kinds of inputs and outputs, the simple I/O and the Xbus. The Xbus is represented by the X pin, so X0 and X1, and simple I/O is just P0 and P1. Simple I/O is mostly analog, so you can have any value between 0 and 100, and you can connect it to simple things like buttons, for instance, and LEDs. And Xbus has a little bit of a protocol, meaning when it writes to something, something else needs to read it. And there are some advantages to that. For instance, you can go beyond the range 0 and 100 because these little devices, this little variable here can hold values from minus 999 up to the positive equivalent. All right. So for this tutorial, we're going to be working with the MC4000. This one down here is the MC4000X. The only difference between those two is that this one has only Xbus connections, while this one has also simple I/O. It's, yeah, half and half. Okay. So let's connect this guy here. Let's put it right in the middle here. We already get a message, a problematic message, because pin type mismatch. This is a simple I/O and it connects fine to P0, but this is Xbus. This does not connect to this guy. You can see that whenever we have Xbus connections, we have this little yellow dot in here. I hope you guys can see in this video. And if not, we don't have the little dot. So this connection is invalid, which is why we're going to connect this device to P1. I can switch views from this track view from the actual view using the tab key. Right? This is a shortcut. Alright, so let's learn about instructions. Instead of showing you guys instructions one by one, I will just use them, and I think this should be more effective, right? The first instruction we're going to learn is the MOV instruction. So it's basically one instruction and 1 or 2 or 0 parameters. We're going to use this instruction to copy or move values from one place to the other. So we're going to move the value of P0 to P1. What does that mean? So P0 is this pin. So whatever comes inside this pin, which is the output from this button, we're going to move it to P1, which is the LED, right? And rule number 1 of microcontrollers is you always have to sleep. So this is the sleep instruction, and we're going to sleep for 1 cycle. We can sleep for 2 cycles, 200 cycles, whatever. The minimum is 1. There are special cases where we want to sleep for 0 cycles, but let's not talk about that for now. Okay, we can run the simulation now, and as you can see, whenever we press the button, we are moving this value into this one. So not much difference compared to a simple wire, right? Okay, time to start making things interesting. Let's stop the simulation and erase this code. So let's try to figure things out. We want to make this thing work as a T flip-flop, right? So the first thing I want to do is to try and model the behavior of this thing. So most of the time, a chip like this would be doing nothing. It would be sleeping and waiting for any inputs. All right, so we're going to learn condition instructions now. So we're going to learn how to compare things. So for this, we use the test instructions. So TEQ means test if equal. So if P0 equals 100, it means that the button is pressed. And if the button is not pressed, then P0 is 0. So if P0 is 0, meaning there is no input, then we're going to sleep and we're going to jump back to waiting. So let's create a label here, and yeah, this should be already clear to some of you. So wait, so if P0 equals 0, so no button pressed, we sleep. We use this plus sign to execute instructions when the test succeeds, right? If the test is true, then whatever is followed by a plus sign gets executed. If the test fails, whatever gets followed by a minus sign gets executed. This is how the logic here works. So we will just be sleeping. So nothing happened, sleep, and go back to testing. Nothing happened, and so on. Okay, whenever the button gets pressed, we break out of this loop. Okay, the accumulator always starts at a value of 0. And one thing we can do here is to test again. So now, if we break out of this loop, we know 100%, we're 100% sure that the button is pressed. So what we want to know is, if the value of the accumulator is still 0, then we want to move 1 inside the accumulator. All right. If this is not true, then we want to move 0 inside the accumulator. All right. And now what we can do is to run maybe yet another test. So if the accumulator equals 1, no, let's not do that. Let's just move the value of the accumulator. Let's move the value of the accumulator into P1. So there's going to be a little bit of a problem with that, not much of a problem, but this is going to teach us how to deal with this. So whenever we press the button, we break out of the loop, right? And then we switch in here. This is how you do comments, by the way. You use the hashtag. We switch the value inside the accumulator, and then we move the accumulator in there. So if it's active, it's going to become inactive, and vice versa. Let's run the simulation. We press the button. Yeah, you can see that it dimly lights up in there. There's a small change, and that's because the value that we are trying to send to this bus is very small. It's just a 1. We can send a 100 instead, and not 1000, 100 instead, and make this very bright. So let's run the simulation again. So now you see, now it's very bright, and we press the button again, it turns off. But there is still a problem. Sometimes it kind of fails, as you can see here. It won't respond correctly. And if I hold the button, it starts blinking, which is not exactly what we want. So let's try to sort this out. Okay, so let's stop the simulation and go for another solution. Let's get rid of this comment, and now you will learn another instruction. So those 3 instructions, they actually can be done with a single instruction, which is the not instruction. The not doesn't require a parameter, so we're going to not the only variable we have, the accumulator, but not always applies to the accumulator, even if we have more variables. And I'm telling you this because there's this other big guy in here, and it has an extra variable. All right. So what this does is, when we run not, if the value of the accumulator is 0, it becomes 100. If it is 100, it becomes 0. So 3 instructions in 1. Awesome. Okay, so we do the inversion, and we move this in there. So the problem, the entire problem was that when the button is pressed, the test fails. So we never sleep, and we don't jump back. We invert the signal, we send the output, and then we go back here immediately without sleeping. But the button is still pressed, so the test fails again. So it doesn't sleep again, and it goes back inside the loop. So we need to sleep here somewhere. One of the solutions that we can do to this is to add a simple cooldown. Let's add a cooldown of 4 in here. So whenever we press the button, we do the inversion and the output, but we wait 4 time units before we do anything else. So let's run the simulation. We press the button, and now, yeah, as long as we keep giving it proper clicks, it doesn't fail. It won't ever fail. So this is a good and interesting solution. But if we hold the button, it starts blinking, which is not exactly what we want. Maybe we want this, maybe we don't want this. But yeah, I would say that for a T flip-flop, this is not desirable behavior. So now this time we're going to check if P0 is 100. So we know that, remember, in this section of the code, the button is pressed. We're going to check if the button is still pressed. And if it is, we're going to sleep and we're going to jump back to wait 2. Yeah, our second wait loop. So let's put this in there. Okay, let's see what happens now. We press the button. It works as expected. It never fails. Awesome. And if we hold the button, see that it gets the code gets trapped inside this loop. And when we release the button, the code gets trapped inside this other loop. So this is a kind of interesting solution, and it completely sorts out our problems. But there is still a more interesting or smarter solution that we can apply to this. So let's try this out. Stop the simulation and let's erase everything. So now, instead of just sleeping all the time and waiting for the button to be pressed, we are just going to check if the button is pressed. So if the button is pressed, we're going to invert the accumulator. We are going to move the value of the accumulator to P1. By the way, you don't have to keep moving the same value inside this bus all the time, guys. Once you move a value into a simple I/O, it stays there until something reads from it. More specifically, until the chip itself reads from it. If another microcontroller, like right here, reads from it, it will not erase the value on P0. This piece of information will become useful eventually. So what we want to do now is we also want to sleep, and we want to test again if P0 equals 100. And if it does, we're going to jump back inside this loop. So let's label this in here. So check this out, guys. Button is pressed, all right. Invert the signal, send the output, sleep for 1 second, and check if it is still pressed. If it is, keep looping in here. So it doesn't matter if we hold the button or if we give it a short click. It will be trapped inside this, so it will not keep inverting this thing and making our T flip-flop inconsistent. Okay, and when we release the button, this will test and nothing will be executed. Maybe some of you are already able to see the problem in here, because this instruction will get executed. And since the button is released, it will fail, so it will not execute anything in here. So it will never sleep, because there is no sleep instruction. So what we can do is to just add a sleep down, here at the end that always gets executed. Another possibility is to just get rid of this plus sign. So the sleep happens whenever no matter what the input is, which is a better solution in my opinion. So let's run the simulation, press the button, things get inverted, and yeah, this is actually acting like a proper T flip-flop. Let's hold the button. So yeah, it doesn't do anything. Let's hold the button again. Yeah, it changes only one time and it doesn't do anything. It gets trapped in the loop as expected. It doesn't execute a lot of instructions. So this is kind of power efficient as well, because most of the time it's not doing anything. So yeah, this is a very good solution, guys. And this was your introduction to microcontrollers. With those instructions, you can do a lot of stuff, guys. Trust me, you know how to deal with pins. I will tell you more about Xbus in our next tutorial, and there are more instructions to be learned, and even hidden instructions, like secret instructions that eventually will get unlocked in the game. I don't want to spoil those for you. This is why I'm going to talk about those in a separate video, guys. I hope that you enjoyed. Feedback is always appreciated. Thank you very much for watching, and see you next time. Bye.